The product that we, Section062 Team 1, have created is what we call the Active Filter Feeder Simulator. It's a product that we created for the Center for Aquatic Sciences as a tool for their classrooms to show children and other K-12 students the concept behind how oceanic animals such as whale sharks filter food out of the water. So the natural science topic of the project is the actual filter feeding done by the animals in their mouths. It's done by inhaling water at a high velocity, and as the water flows through, krill and plankton and other food sources are retained. The applied science of the project here is that there's a change in pressure that allows the water to flow from a high pressure to a low pressure environment, and this is due to the high velocity at which the water is being inhaled by the animal. Seen here are two pictures of our final product concept. The top picture is the overall product, and the bottom picture is a closer look at the interior of the product. It's a physical representation of the animal's mouth, and the concept is that the teacher or whoever is performing the lesson can pour water that has a proxy food in it into the interior piece, which is pictured at the bottom left, and the water flows through valves that are on the wall of this interior piece, which is a representation of the animal's gills, and the food that is within the water being poured will be retained, which will show the students how water is able to be poured through, but the animal within its mouth is able to retain the food.
Functionality. What it should portray. The function of a whale shark filter feeding, also called raking, will be shown by pouring dirty water into the smaller container. The smaller container will represent food being filtered through the gills as the whale shark inhales. The water will have a higher pressure than the surrounding water in the larger container. This will allow for proper flow through the smaller filter, which will represent the gills. This will leave food particulates inside the mouth of the whale shark, while allowing the water to drain through. Execution. The number of valves and the size of the valves will be used to create a pressure differential. This pressure differential will affect the direction in which water will flow. The size of the valves need to be large enough to let water through, but also small enough to not let any of the food particles in. The valves must also be an appropriate size to do so without clogging. The size of the larger container needs to be able to hold all water, but also hold it at a lower pressure than that of the smaller container. For the supports, the wires of the small container must be able to withstand the weight of the container while water is being poured into it.
There are two key experiments that are done to test out the functionalities of the concept. The first experiment is to measure the flow rate of water. The procedure is to close the valves on one side of the filter, then the time for the filter to empty the water is measured. The step is repeated for 2, 3, and 4 sides of valves closed. This experiment is to determine the best flow rate of water pouring out of the filter. The second experiment is to measure the percentage of valves clogged with different particle sizes. The first step is to prepare different sizes of particles and put them with water in the filter. Then the valve of the filter is observed and the number of clogged valves is measured. This is to simulate the active feeding of the whale shark.
Alright, for the experimental results, the first thing we tested was the diameter of the particles and see the percentage of the valves that would be clogged depending on the size of the particle. So we tested the diameter from 0.1 to 0.5 inches, and the percentages varied to where the worst percentage was 18.75% for a half-inch diameter of a particle. That being because we drilled the holes a little bit bigger than a quarter inch, so they covered up all the holes in the bottom. Out of 32 holes, it covered up all the holes in the bottom, and it didn't drain any water through the bottom. Next, we tested the number of valves. As you can see in the video, I'm showing you right now the check valve that we use to check. They're a quarter inch. One side stops the water or the backflow of water, and the arrow points in the direction that allows flow of the water. we checked the number of valves anywhere between 8 and 32, and we poured the same amount of volume of water into the small container and timed the amount of time it would take for the container to be completely empty. As it made sense that the more in the valves, the faster the container was able to drain. So that would depend on the stakeholder using the apparatus to teach the students how fast they would want it to move, so the students would accurately understand what would be going on in terms of the natural and applied sciences. So for the analysis of the experimental results, the size of the holes did not matter when the valves were installed. The valves were sticking up slightly from the surface of the holes in the container, so they actually pushed away the particles while still allowing water to flow through, versus when there was just holes there and we were doing the tests with the particles kind of like would fit into the holes and sink into them, and that's what caused the clogging in the bottom. The number of the holes and the location of the holes mattered more than we expected. The number turned out to be similar to what we expected it to when determining the speed, but the location of the holes mattered, as like when we didn't put holes in the bottom of the small container, there were still holes left in the bottom of it. And lastly, we didn't really talk about this during the experiment, but the epoxy was strong, it held together well, and you could put forces, and the boxes that we made held together strong, but it was really hard to create a watertight seal. If you look in the video that I'm showing right now, you can see that we had to use duct tape to cover up any little cracks or holes that we had because of the epoxy material not being applied correctly. So for future use of this prototype or future prototypes into the final product, there would need to be a better way to create an interlocking system to make both containers watertight. Alright, so lastly, this is a video of the water actually moving through the valves set up in the small container into the bigger container. There were still some holes, so it was hard to get an accurate analysis and experimental data, but you can see in the back how the holes were the valves in the back were creating the flow of water that we wanted, and the water would, if the water level was higher, it would flow out the sides. But for testing purposes and for this video purpose, we decided that it was easiest to show it from the bottom.
In conclusion, filter feeder simulator meet the needs and specifications for stakeholder needs. The filter feeder we designed does meet all the specifications and need we listed for stakeholders need, which is it has to be easier for K-12 student, easy to transport, safe, low maintenance. All those needs did meet our filter feeder simulator. Filter feeder does explain the natural and applied sciences according to the specifications, as the filter feeder we designed meets the natural science, which is it explains how it works within shark's mouth. Also the applied science on the low and high pressure, which is caused by the velocity. It explains both the natural and applied sciences concepts. Further research and development within the product will make it more easier to teach K-12 students about how it works in like real world and how it works in animals' mouth. We just need some of the further research and development within the product to make it more easier to teach the K-12 students. But the product does meet all the expectations and needs. The product should get accepted.